How you guys doing today? I'm going to be showing you an old exam of mine from the third exam, chapter 6, 7, and 8 in thermochemistry, quantum mechanics, and electron configuration and orbital diagrams. I'm going to start off by showing you just the exam. If you want to, you can freeze this. So that's the first page I'll be talking about. The second page will be right here. This is the third page. And then here is the fourth page. And once again, this is available on Moodle for my students, and it will, in the exam, it would be accompanied with all the formulas and the periodic table. Okay, the first problem is parts A through C, and it says to determine if the following is an exothermic or endothermic reaction. So for number 1A, what we get, for 1A, it says an ice pack on someone's Achilles. And the thing to remember is the Achilles is the system. So in this case, we can think of the ice pack goes on the Achilles. It's cold, so it's going to pull heat from the Achilles. So the Achilles is actually giving off heat. So in this case, the answer would be exothermic for the Achilles. If we were talking about the ice pack would be endothermic because it would be taking in heat. But since the Achilles is the system, it's going to be exothermic in this case. For part B, what we have is ice melts in a soda, and the system in this case, ice is the system. So in this case, once again, the soda is getting cooled down, the ice is getting heated up. So the ice is absorbing heat from the soda. So in this case, it would be an endothermic reaction. For part C, it says water condenses on a leaf. Okay, and water is the system. In this case, it's kind of hard to think about what happens in condensation. Is heat released? Is heat absorbed? But it's pretty easy to think about when water is evaporated. And when water is evaporated, it is absorbing heat. So evaporation is an endothermic process. So condensation should be an exothermic process, and that's the way that I think about it. Okay. Number 2 is, what is the energy of a photon when it relaxes from a 5d orbital down to a 2s orbital in a hydrogen atom? Okay, so remember we talked about in class, we only can calculate the energy of a photon in the hydrogen atom. It's a very simplified system. So what we'll be using is we'll use the equation negative 2.18 times 10 to the negative 18 joules times 1 over n final squared minus 1 over n initial squared. Okay, so the only thing we have to think of is this is initial. It starts off at 5d and it ends up at 2s. So we're only going to look at the n value in this case, and the number in the front of the orbital is the n value. So what we would do is we would do 1 over 2 squared minus 1 over 5 squared, which is 1/4 minus 1/25. And then when we multiply this by negative 2.18 times 10 to the negative 18 joules, what we end up getting is negative 4.578 times 10 to the negative 19 joules. So what this tells us is when that electron relaxes from a 5d orbital down to a 2s orbital, this negative sign tells us that it releases heat and it releases energy in a photon of light. So part A of this question was, what is the energy of that photon of light? This negative value just tells us that that energy is released, and this is the amount of energy associated with it. For part B, it asks, what is the frequency? And actually, on that, the test I showed you in the beginning, it said in nanometers, but frequency should be in hertz. Okay, so I'm going to give us the answer in hertz, and I'm going to just erase over here to do this problem. So we're going to use the equation E equals h nu. So let's use E equals h nu. And if we rearrange this, we want to solve for nu, so we get nu equals E over h. So if we just plug in these values, negative 4.578 times 10 to the negative 19 joules divided by h, which is Planck's constant, 6.626 times 10 to the negative 34th joules seconds. Notice how joules cancel. The units will be in 1 over seconds, which is equal to hertz. And this gives us a value of 6.91 times 10 to the 14 1 over seconds, or 6.91 times 10 to the 14 hertz. You might wonder why I didn't make this negative. And the reason is there's no such thing as a negative frequency, okay? We can actually leave out this negative sign here. That negative sign just tells us the direction in which the energy was either being absorbed or emitted. In this case, it was emitted. We do not need to use the negative sign here, so you never have a negative value when we're talking about frequency. Okay, moving on to number 3, you can see this makeshift periodic table showed up for electron configurations on number 3, as well as orbital diagrams for number 4. We need to use the periodic table. So for number 3, A, it asks us to find the electron configuration of magnesium. So what we do is we find magnesium. Magnesium is located right here. And as you can see, I've kind of color-coded the periodic table. Everything that I've drawn in yellow represents the S block. Everything that I've drawn over here in blue represents the P block. What I've drawn in pink is the D block. And what I've drawn in orange is the F block. Okay? And the numbers that we start with can be figured out using Chapter 7 concepts of quantum mechanics. The S block starts with 1, the P block starts with 2, the D block starts with 3, and the F block starts with 4. So with magnesium, we see magnesium's located right here. And when we see that, we can see that this is the 1s is hydrogen and helium, 2s, 3s. So it ends with 3s2. And the way I like to do electron configurations is I like to work backwards. So 3s2 is what the magnesium, 3s2 is what magnesium ends on, okay? If we work backwards, below that is 2p6. Below that, so this is 2p6. This is 2s2.
Something happened.
Shh. Get away. And the one below that is 1s2. So this is the electron configuration for that. So this is the electron configuration for magnesium. 1s2, 2s2, 2p6, 3s2. So if we look at it, it goes 1s2, 2s2, 2p6, 3s2. And that's the electron configuration for magnesium. For selenium, for part B, and this is the full electron configuration. Now, with the noble gas shortcut, we can go to the noble gas nearest to magnesium. So we go backwards 1, 2, neon. Another thing we could do is we could put neon in brackets. And what that represents is everything up to 1s2, 2s2, 2p6. So we could just simply write for magnesium neon 3s2. Either of these are good. For selenium now, it's located right over here. So this is in the P block, and once again, the P block starts at 2, so this is 2P, 3P, 4P. So this is going to end in 4P, 1, 2, 3, 4. So for selenium, it's going to end at 4P4. Working backwards, 3D10. Below that, it's 4S2, 3P6, 3s2, 2p6, 2s2, 1s2. So this would be the electron configuration for selenium. Once again, using the shortcut, the noble gas closest behind it would be argon. So if we put argon in brackets, that represents everything up to 3p6, so that represents that. So instead of writing all of those, we can just write argon, 4s2, 3d10, 4p4. The next one is actually an ion, and it's Fe3+. So if we look at iron, iron is located right here, and if we were to do iron as a neutral molecule, it would be ending in 3D, 1, 2, 3, 4, 5, 6. Now, what does that 3+ mean? That means there's 3 less electrons. So in fact, we would end up going back to 1, 2, 3. So iron 3 would have the same electron configuration over here. So let's just draw out the electron configuration of Fe3+. Or let's do Fe3, Fe normal, and then we'll take away the 3+, and then we'll figure out what's the most stable one. So if we're just doing it for iron, I'll do it for iron underneath here. It ends at 3d6, 4s2, 3p6, 3p6, 3s2, 2p6, 2s2, 1s2. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, okay? Now, the fact that it's actually Fe3+, that means we're going to change this to lose 3 electrons. So it would become 3d3 when it's in the 3+ position. So this would be a pretty good electron configuration for iron 3+. The only thing that we have to realize is half-filled, fully filled, or empty orbitals are more stable than partially filled. So when a d orbital only has 3 electrons in it, that would be 3 of the 10. It's not going to be fully filled, half full, or empty. But what we could end up doing is we could end up taking these two 4s, since actually 4s is actually a little bit higher in energy than 3d. Based on the way the periodic table feels, 4s fills before 3d, but these two are so close in energy, what actually ends up happening is the 4s orbital goes empty, and what we get is 3d5. So the proper electron configuration for Fe3+, I'm going to write it doing the noble gas shortcut from argon. So we're going to put argon in here, and that's going to represent these up to 3p6. And then 4s2 is empty, and we can just write argon. We can go ahead and put 4s0, 3d5. Notice how these two are equivalent in electron configurations, but this one have a full 4s, which is good, but a 3/5 of it. So if we drew the orbital diagram, which we're going to show in a second for the 3d orbital with its 5 orbitals, when we have a 3d3, this is not good or bad because it's partially filled orbital. If we take those 2 electrons over and fill it up to make it like this, what that gives us is a half-filled orbital, which is much more stable. So we can see that this would be the best electron configuration. If you did this, you would still get partial credit on the test, but on this one, this would be what I expect for full credit. For the last one, D, it is Br minus. And if we see Br right here, that means it's similar to selenium. It's going to end in 4p5. But this negative charge means we have 1 extra electron. So it'll end up being 4p6. So we could say it ends in 4p6. So we could write 4p6 as our last orbital. And just to fill up everything below, 3d10, 4s2, 3p6, 3s2, 2p6, 2s2, 1s2. And as it turns out, Br minus has the same exact electron configuration as krypton, so we could have simply just wrote krypton in here. Krypton and Br minus are isoelectronic. And remember, we learned that halogens always like to get a charge of -1 because they always add 1 electron to get the same electron configuration as the noble gases, which are stable. So this is the reason why we see these things all get -1 charges. Things in this row gain 2 electrons to get the noble gas configuration. Things over here lose an electron to go back to the noble gas. Things over here go back 2, etc., like that. Okay, for number 4 is actually the orbital diagrams. So orbital diagrams are very similar to electron configurations. And what I showed when I was doing that Fe3+ one, when I drew those lines, those are what orbital diagrams are. So they're the same kind of things, but let's go ahead and get to it. So the first one we're going to do is bismuth. And bismuth is located right here on the periodic table. So we can think of it as it's ending up in the 2, 3, 4, 5, 2p, 3p, 4p, 5p, 6p orbital diagram. In this case, if we drew the orbital diagram for every single element, it would take forever. So I'm going to use the noble gas shortcut representing up to xenon here. So I'll put xenon in brackets, and that represents everything up to 5p, 2, 3, 4, 5. It represents everything up to 5p6. So what we need to draw then is this here, which is 1, 2, 3, 4, 5, 6. So we have the 6s orbital, and we'll draw that. There's only one 6s orbital. After the 6s orbital, you can see here we have this star, which represents this first row of the F block. So the first row of the F block, if you think back to quantum numbers, is the 4f. So we'll write 4f, and each F has 7, 2, 4, 5, 6, 7. So it represents these 14 elements here. Then the D block, which starts at 3, 3, 4, 5, 5D, which is So 1, 2, 3, 4, 5. And then that brings us to the 6p orbital, which I ran out of space, so I'll just draw it underneath here. The 6p orbital, which fills up, okay? So if we were filling up, according to Hund's rule, we go up, down, up, up, up. So once you get to a degenerate orbital, like all F's, they fill up all 7 in the up, then they start filling down like this. When we get to 5D, we go up, 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 down, 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 down. So that's taking every electron that was 1 to up, down, all the way through to here. Now we have 3 electrons here, so we go up, up, up. So in the 6p orbital, they spread out between the 3 degenerate 6p orbitals, and they all have an up configuration. If you wanted to, you could have done that for every single element up to xenon. That I don't have the time or the energy for that, so I'll let you do that on your own if you would like to. For number, this was 4A. For number 4B, we have cobalt 2+. So cobalt is located, where is cobalt? It's going to be in 3D. Cobalt is located right over here, and it has a 2+ charge. So we see 1, 2, 3, 4, 5, 6, 7. Okay, so once again, we'll do the noble gas shortcut for argon. And then we will see that there is the 4s orbital. And then we have the 3d orbital. So there's 3 degenerate 3d orbitals. So when we're filling up these, potassium is going to be up, calcium is going to be down. 1, 2, 3, 4, 5. These go 1, 2, 3, 4, 5. So that's up to magnesium. Iron and cobalt would go down and down. But notice how we have a 2+ charge, so we actually have to get rid of 2 electrons. Since this one was Colt. Stop that. Since this was, these ones actually make it better because now we have a half-filled orbital. We're good, and this is the orbital diagram for cobalt 2+. C would be for zinc 2+. So zinc 2+ would be this one right here. So once again, we'll use the noble gas shortcut, argon, and we'll do 4s, and zinc ends in 3d. So let's just do zinc the whole way. So let's just do it for zinc. And after argon, it fills up, up, down. And then there's 10 for zinc. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But now when it becomes zinc 2+, what we see is we have to get rid of 2 electrons. If we this is a fully filled d orbital. If we take out these 2 electrons, even though they're technically higher in energy when we fill up, when we take away, instead of taking away 2 here, instead of taking away 2 here, we take away these 2 here, similar to how we saw with iron. And now this is the proper electron configuration for zinc 2+. A fully filled 3d orbital, an empty 4s is much more stable than a fully filled 4s and a 8/10 of the way filled 3d. The last one from this in D is phosphorus 3-. So phosphorus is located right here. Let's first do simply for phosphorus. And in this problem on the test, I asked you to not do the noble gas shortcut just because I wanted you to practice. So let's go ahead and do it. 1s, there's 1s orbital. There's 2s orbital. There's 3 equivalent 2p orbitals. There's a 3s orbital, and then we have 3 equivalent 3p orbitals. So if we're just doing phosphorus, we fill up, down, up, down, up, 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 down, 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 up, down, up, up, up. Now, like I just talked about, phosphorus likes to get a charge of 3 minus. So when it does this, that means we have to add 3 electrons. So we simply add here. And we can see that this has the same electron configuration as argon, which is why P3 minus is so stable. And this would be the proper orbital diagram for P3 minus. Okay, looking at number 5, we can see that the question asks propanol C3H8O can be combusted. Write out the balanced molecular equation for the complete combustion in pure oxygen with all reactants being in the gas form. So what we'll do is we'll start off with C3H8O gas, and in a combustion reaction we add O2 gas, and the products of a complete combustion are CO2 gas plus H2O gas. Okay? If we balance this equation, what we end up getting is 3, 4, 9 over 2. Okay? What you could do is you could multiply everything by 2, but since in this we're going to multiply by the mole ratio, this would be 2, 9, 6, and 8. It'll end up giving you the same value, and that'll be giving it for 2 moles of propanol. So instead I'm going to only do it for 1 mole of propanol and leave that 9/2 in here. In this case, that will be okay. So this would be the balanced equation for this. The equation that we'll use for this problem is we'll use the equation where we take the summation delta heat of reaction is equal to the summation of NP delta heats of formation of the products minus summation NR times the heats of formation of the reactants. Now, all this means is we add up all the products and we subtract out all the reactants. So what we'll do here is we'll take the products 3 times the delta heat of formation of CO2 plus, stop it, 4 times the heats of formation, shh, stop it, 4 times the heats of formation of water, put that in a bracket, and we'll subtract out the heat of formation of C3H8O plus 9/2 times the heats of formation of O2. Okay, so let's go ahead and plug in our values. We have 3 times CO2, which is negative 393.5 plus 4 times negative 241.8 minus 1 times the heat of formation of this, which is negative 302.8 plus 9/2 times 0. How do we know this was 0? A, there was no value for O2 on here, and also because oxygen is in its standard state, so anything in the standard state has a value of 0. This gives us a value equal to negative 1844.9 kilojoules per mole of C3H8O. If we had happened to multiply this whole thing by 2, what it would have gave us is, if we did everything times 2, when we put in all the values times 2, it would have gave us a value of delta H equal to negative 36 89.8 kilojoules, but that would be per 2 moles of C3H8O. Okay, so the answer we want, per 1 mole of propanol, it will release 1,844.9 kilojoules of heat per 1 mole of it reacted. Technically, this question should be saying, it's written wrong. What kind of teacher does that? The question asks, why does sulfur have a lower ionization energy than phosphorus? And generally, the trend says that as you go to the right of the periodic table, ionization energy should increase, and that's a general trend. But if we look at this, the way we can answer this question is if we look at sulfur and we look at phosphorus. Let's actually put phosphorus on this side. So phosphorus is on the left of the periodic table of sulfur. So if we draw the orbital diagram for phosphorus, orbital diagram for sulfur, this is 3s, this is 3p, this is for phosphorus, this is 3s, and this is 3p for sulfur. For phosphorus, this is the electron configuration for phosphorus. For sulfur, this is the electron configuration for sulfur. So usually it's harder to take off an electron to elements further to the right. The reason is phosphorus has a half-filled 3p orbital. So to remove one electron is going to go from a half-filled orbital to a partially filled, which is not stable. With sulfur, it has 4 electrons in the 3p orbital. So if we remove this electron right here, it goes from a partially filled to a half filled, which is much more stable. So this kind of shows why the general trend doesn't hold true when we go from phosphorus to sulfur. Let's go ahead and take a look at number 7. Number 7 says, arrange the following isoelectronic series in order of increasing atomic radius. Okay, so we have calcium 2 plus, S2 minus, argon, potassium, and Cl minus, okay? Isoelectronic just means that all of these, and if we look on this periodic table, we can see calcium 2 plus means it has the same number of electrons as argon. Potassium plus loses an electron to be the same as argon. Chlorine minus adds an electron to be the same as argon. And S2 minus gains 2 electrons to have the same as argon. So all of these would have the same electron configuration of argon. All of these would have the same electron configuration, okay? So let's determine which one would be the smallest and which one would be the biggest. Well, as it turned out, if we think about it, calcium, which has an atomic number of 20, so this has an atomic number equal to 20. So that means it has 20 protons in its nucleus, but 18 electrons going around. Potassium has 19 protons in its nucleus and 18 electrons being pulled around. Argon, 18. So if we're looking at argon, 18 protons, 18 electrons being pulled around. We can imagine that the 18 electrons all getting pulled in, 20 protons will pull this in the most. So we should see that calcium would be the smallest in atomic radius. Okay? Since potassium has 19 protons pulling in 18 electrons, it would be the second smallest. Argon has 18 protons pulling in 18 electrons. That would be next. Chlorine has an atomic number of 17. So it has 17 protons being pulled in, or 18 electrons pulling in by 17 protons. So that'll get spread out a little bit further. So chloride would be there. And then if we look at, sodium or sulfide, it would have 16 protons pulling in 18 electrons. So those would be spread out the most. So sulfide would be the biggest. So this would be the largest atomic radius. And calcium 2+ would be the smallest. So the thing to remember, or atomic or ionic in the case of all of these ions, okay? So the take-home message is, if everything else is the same, cations are smaller than anions because they have more positive charge pulling it in. Okay, moving on to number 8. Number 8 says, according to the balanced equation, C8H18 plus 25 halves O2 makes 8 CO2 plus 9 water, and this has a delta H equal to negative 5,450 kilojoules. Colt. So an Eskimo wants to warm up his igloo by burning octane.
Put my foot on it.
Stop it. The question says, an Eskimo wants to warm up his igloo by burning octane according to the above reaction, and if he needs to generate 975,000 kilojoules of energy to completely heat up his igloo, how many liters of octane does he need to burn? Assuming 100% efficiency, and we're going to say that octane's density is equal to 0.703 grams per milliliter. Okay? So we want to generate this much energy. What this equation tells us is that for every 1 mole of octane, 5,450 kilojoules of energy will be released. It also tells us for every 8 moles of carbon dioxide, 5,450 kilojoules of energy will be released. For every 9 moles of water produced, it produces this. So this is all one big stoichiometry problem, okay? So if we start off with 975,000 kilojoules of energy, we can use stoichiometry and say, since we have, and since we want to produce, we'll put a negative sign here, okay? And we'll show why that is so that you don't get hung up on the negative sign. For every 1 mole of octane that we burn, we produce 5,450 kilojoules of energy. So kilojoules will be canceled. That tells us how many moles of octane we would need. We would then need to know for every 1 mole of octane, it has a molar mass of 114 grams per mole. Now we can use the density. For every 0.703 grams of octane, it has a volume of 1 milliliter. And the question wanted to know how many liters so that's why we're going from grams to mil. If we just needed to know grams, we could have stopped right here. We need to go to liters, so we use the density in grams per mil, and then we convert mils to liters using 1 liter is 1,000 milliliters. And we can see that moles of octane cancel, grams cancel, mils cancel. That gives us a value of 29.0 1066 liters. Based on sig figs, this problem had 3 sig figs, 3 sig figs, 3 sig figs, 29.0 liters of octane would be how much that Eskimo needed to burn to do that. Okay? Next problem, number 9. Which of the following orbitals cannot exist? A, 7s, B, 5f, C, 2d, D, 8g, or E, 6f. Okay? So if we think about this, the s orbitals start off with 1s, the d orbitals start off at 2d, the p orbitals start off at 2p, the d orbitals start off at 3d, the f starts off at 4f, the g starts off at 5g. So looking at this, we can see 7s, it starts at 1s, there is a 7s. F, it starts at 4, so there is a 5f orbital. D starts off at 3, so there's no such thing as a 2d orbital, so that would be the answer. But just to verify, is there an 8g? I mean, we don't have any elements that fill the 8g in the ground state, but there could be something that goes up to the excited 8g state, since g starts at 5. Once again, 6f, it starts at 4, so that's why the answer for this problem is 2d. So for number 10, which has higher energy? And we look at this, and for A, it says light with a wavelength equal to 760 nanometers, or light with a wavelength equal to 4.7 times 10 to the negative 7th meters. Okay? So what we'd have to do is get these units in the same thing. In the case of this, we could convert this over into nanometers, and this would be equal to 470 nanometers. So what we have to decide is light of 760 nanometers or 470 nanometers higher in energy? Remember, the bigger the wavelength, the lower the energy. So this has a larger wavelength, so we would say that this one has a higher energy. Okay? For B, it says light with a frequency of 4.5 times 10 to the 14 hertz, or light with a wavelength equal to 1800 nanometers. So what I'll do is I will use nu equals c over lambda, and when I convert this, that's equal to 3 times 10 to the 8th meters per second. We have to convert that into meters, so that gives us 18 times 10 to the negative 7th meters, and that gives us a frequency equal to 1.66 times 10 to the 14 hertz. So the higher the wavelength, the longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. In frequency, it's opposite. The higher the frequency, the higher the energy. So this one would have higher energy. Okay. For number 11, it is a question where it says, if you have a 1 kilogram rod of each of the following metals from the table, and you had to stick it in a fire, which one would you choose if you needed your rod to get to 500 degrees Celsius the fastest? Explain yourself, okay? So the different substances we have are gold, copper, aluminum, silver, Pyrex, lead, and water. I don't know how you're going to have a water rod, but, you know, this is just a conceptual problem. The specific heat of each of these metals in units of joules per gram degree C would be 0.126, 0.377, 0.921, 0.239, 0.753, 0.126, and 4.184. So in this problem, we want to see if we took a rod of this and we stuck it in the fire, which one would heat up to 500 degrees fastest. So we have to think, which one is going to heat up the fastest? The thing with the highest heat capacity or the lowest heat capacity? As it turns out is, if we want this something with the highest heat capacity to heat up by 1 degree, it's going to take 4 joules of energy. So it's going to take a lot of time because the heat's coming in at the same time. Something with the lowest heat capacity is going to heat up the fastest, so our answer should be either gold or lead, since they have the same specific heat capacity, and it's the lowest of all 3 on this list. So that's going to be how we answer that one. So what we see is, if a cylinder has 400 or 4,345 joules of work done to it, and releases 214 joules of heat due to friction, what is its change in internal energy, delta E? So we're going to use the equation delta E equals Q plus W. This is Q, this is W. All we have to decide is what the sign of the work is. So a cylinder has 4,345 joules of work done to it. It either can do work to something or it can get work done. Since it's getting work done to it, that's going to be a positive. So positive 4345. And since it releases 214 joules of heat, it can either release heat or absorb heat, get back. This is going to be negative, so negative 214 plus 4345 would give us positive 4131 joules of work would be the answer, and that was a multiple choice question, and you can do that. Okay, let's go ahead and look at extra credit problem number 2. Extra credit problem number 1 is an open-ended question. Describe the invention that you have been thinking about that could revolutionize the world. Explain in terms of how the chemistry would work. Up to 3 points, depending on how awesome it is. Really, I'm just trying to steal your guys' ideas, but obviously I would share the credit with you. But for number 2, it says, if we were able to continue making new elements. So right now we have elements up to element 118. If we were to continue to make new elements, what would you expect the atomic number of the first element to occupy a 5G orbital? Okay, so this takes a little bit more thought, okay? If we think about it, what you have to realize is, notice how this F orbital is sandwiched in between this here. So if we look at the numbering, it goes 87, 88, 89, 90, up to 103, 104, all the way up to 118. That would mean that element number 119 would be right here. Element number 120 would be in the 2, 3, 4, 5, 6, 7, 8s orbital. So it would go like 8s2. And then what I believe is, since like if you notice, there's like 2 rows of p orbitals before the d's show up. Then there's 2 rows of d orbitals before the f show up. So what I would assume is there would be the 2 rows of f orbitals. So the next element would be element 121, was the answer I was looking for, would be the first element in this 5G orbital, 5G1. The 5G orbital would contain 18 electrons, or there would be 9 5G orbitals, you know, so there would be a row of 18 electrons making a row, which would kind of sandwich in right there. So the answer I was looking for the 5G, the atomic number of the element, the atomic number for the first 5G element would be element number 121. So because I would say that, I would have a third star here where we would have a row of 18 elements. So there'd be 18 of these. And the first one would be 5G1 all the way up to 5G18. Hope you guys got some good review for the exam. As I said, be ready for the test coming up next week. It's going to be of a different format, but if you can do all these problems, you should be good on being able to do the test next week. Study hard, be ready for the test. You guys have a good one. Aloha. Put your face in there. Oh. Smile. Sing a song.
Oh, this is the greatest.